Welcome to a Saturday. I am doing a video for one of the requests on the channel. Someone was asking for more information about this, and then they asked for could I do this on a Raspberry Pi instead of a microcontroller. So I converted everything over to that. So in order to do all this, you're going to need a few things. First of all, of course, you're going to need a Raspberry Pi. Right here, I have a Raspberry Pi 3. This Pi I brought home from work because I was having trouble with the GPIO, this gray ribbon cable. Now, at work, I had loaded the OS on here as 64-bit. I highly suggest you load it as 32-bit. It seems that something was not right in GPIO land in 64-bit. So, be careful of that. Another piece you're going to need is something to pin to the GPIO. Now I chose this guy right here. This what those call a T-bar for GPIO pins for Raspberry Pis. You plug them into your breadboard, you plug the ribbon cable into your Pi, and thus you have a breakout for all the pins. And it's kind of easier to work with. Third, of course, you're going to need the RGB panel, this guy here. We'll talk about this one in a bit. So this one here, I found is not easy to work with, simply because it is simple to build, but not simple to control, right? If you want to be up and running with a variable color grid of LEDs, there are better ones to work with than this one. But we are still going to go through it, and I'll show you how far I've gotten with it and the stage I'm at with the thing, what problems I'm still having with it. Now you also need some sort of method to talk to your Raspberry Pi. Now what I'm using is Visual Studio Code's Remote. It's an ability for Visual Studio Code to connect to the Raspberry Pi, drive the environment over there, but you do the code editing over here on the PC. Now I'm going to slide this Pi over there just to get it out of the way. We're going to just leave. I have to be very careful about this. Okay, so that we have this visible to us. Now, when you prep the OS on the Raspberry Pi, after you install it, you put it on a key. You're going to need a tool to do it. Either one of those, card readers or whatever. I found this guy handy on. Let me just turn the brightness a little bit more up. There we go. This guy here is an adapter, and this is a USB-C writer, like so. Okay, you stick your little micro SD card in here, you stick it in your USB hub, and you flash. Just use the Raspberry Pi imager to put the OS down. Now once you have the OS down, you're going to need to do a few things. Now let me see if I should still have it open. I don't. Let's see if I can connect. Yeah, okay. So I'm going to flip over to one of these desktops that should have all of them on there. Let's borrow this one here, and let's borrow. I thought this one did. Or is this just strictly code? Yeah, this is code. 3 is the desktop, but I think we're on the wrong desktop. Let's properties. Let's go change that. No, not that one. That one. So what you want to do in here, this is the Raspberry Pi desktop as seen through VNC. So you're going to have to set this up. Okay. So if you go up into the menus here in Preferences, Raspberry Pi Configuration, on a brand new install. Come on. There. So after you set everything up, I just had it auto log in. Display, I didn't really have to do anything. This is the key one, interfaces. Turn on SSH, turn on VNC, turn on SPI. You don't need any of the rest. Okay? Even the remote GPIO you don't need. So once you have those ons, and you've saved it and rebooted, okay, you can actually go and, is it visible here? We have to scroll the screen a bit. You want to tune VNC. Now I suggest when you set the VNC, if you right click and you say options, okay, do no encryption VNC password. Okay, that'll make it the easiest to connect to this. And if you do VNC password, you'll have to go to users and permissions, standard users, and you have to give them a password. Okay, once you've done that, you can now VNC into the Raspberry Pi's desktop, and you can also SSH into it, which is what we're going to use for forever after. This is only here for me to get access to some of the settings and stuff, just in case I need to get to it. And I'm just using what's called Reminia, the overall VNC, RDP, whatever you wish to connector client. It's handy, has a bookmark space, blah, blah, blah. So I'm just going to close this. So down in the corner of VNC, Visual Studio Code, there's this guy down here in the bottom left corner. When you actually connect this, and actually I'm going to open a fresh Visual Studio Code so I don't kind of break this one up. When you're actually in here and you press this blue connect button, it'll ask you to do this. I want to connect to a host. And you can add your own host in here. So you can add an IP address, set it up. You can also put keys in too. And I recommend you actually do that, otherwise you'll be answering the login prompt all the time. Now, if you do keys, do remember that on the PC side, you got your private key and your public key for SSH. But on the Raspberry Pi side, and I'll just go there. You're going to have an authorized keys file, and you're going to have your public key. This public key needs to be inside the authorized keys file. Now, you could rename the public key to that. That's not my preferred method for doing this. I always like to know that I have the public key over there. Once you got this, and you can successfully SSH to the account on the Raspberry Pi without getting prompted for the password, and your keys are all working, then you can flip over to Visual Studio Code and try the connection out. You should be able to connect just fine. And then I went in there, I found the folder where I had some test code for playing all around with this. And now I can actually basically run the code in here, step through it, do stuff like that. But downstairs in the Raspberry Pi, I don't have to do anything. But I do have a shell prompt open to there. So you can actually see here, this is where I had all the test code. So there's the same test code over there. Now, so instead of going, running Python 3 space test4.py and pressing enter and running the code from the command line, I am doing it all from the Visual Studio Code's environment using their run without debug, for example, mode. That's what these buttons up are here. That's restart, that's pause, that's stop. But you get the idea. That's stepping in and stepping out of code, stepping over code. Okay. So let's just have a look. I'm going to stretch this window a little more this way, and this lower window a little more this way. So we have a kind of a look at what's going on in here. So this type of matrix, and you can see I'm pointing to it in the bottom right corner screen. Okay, this sort of screen, and am I on the main one still? Yeah, I'm on the desktop. Let me flip over to console. There's a bigger picture of what I'm doing. We have what's known as shift registers on here. These 4 black chips. You can see them right there. Shift registers are otherwise known as Texas Instruments 74HC595s. If you check the data sheet out for them, which is one of the first things I did, because Raspberry Pis, unlike the microcontrollers, do not handle 5-volt controls from a 3.3 volt pin. They don't like it. Okay, so that is one of the reasons. Before I was working on a different project, I had this little guy here, and it is a level shifter. It shifts logic from 3.3 to 5 volts and back again. But I wanted to check to see if I actually needed this for this. And what I did is, if I have the browser window, and if I go to the web page, which is of course not visible, but I will make it visible right now. Every time you restart OBS and do fiddly things, it loses track of which screens are which. Not that one. Not that one. There should be another Chrome. Where's the third Chrome? No, it's definitely not that one. Give me a sec here. I just got to find the right browser window here. And I am on a PDF. I see 2 of my 3 Chromes here, but I don't see my third one. Well, I can't seem to find the third Chrome. Just hold on a sec. That's called move a tab over to the other one. Come on, cut it out. Apparently, it doesn't like me. Okay, just give me a moment. I will fix this. You go back onto this browser. I don't know why it's not going on that browser. I can always get this. Control A, Control C, and onto this browser. Control V and enter. There we go. So this is the data sheet for. Well, you cut it out. I hate all those propaganda prompts. And blow up, blow up, blow up. There we go. So what we're interested in this one, and I think it's okay now, is this bit right here. So this can handle 2 to 6 volt logic signaling to it. I mean, the idea is you have to send a signal down one of the control pins to trigger the shift register to dump its load, right? So, so what we're doing here is, now this code is full of notes to myself and things like this, okay? So you'll see a lot of remmed out remarks and stuff like that, and remmed out code. So once I had everything set up and I was connected, I pulled out the code off the microcontroller and I adjusted it to run on the SPI of the Raspberry Pi. Because in SS, this is interfaced via SPI. You have voltage, you have ground, but you have what's called clock, CE, and MOSI. Sometimes the CE will be called CS. But basically the clock, it times everything. The MOSI is main out, subsystem in, or whatever you wish to call it. Basically, it's the direction from the Raspberry Pi to the LEDs. MISO, or whatever, is the other way around. It's from this guy to that. There's technically 4 wires in SPI. We're only using 3 of the wires. And then, of course, voltage to drive everything. Now, be wary when you drive some of this stuff like this with the SPI. This board is small enough and doesn't use that much current, so we're within the range of what the Raspberry Pi can supply. But if you use something bigger, like an LED strip like this here that I'm showing in the corner window, this thing can overdrive the voltage the current on your Raspberry Pi. So you need to have an auxiliary voltage supply on it. Otherwise, you can burn the pins out on the Raspberry Pi, so be careful of that. Now, once we have everything hooked up, I told in the code right here, clock is pin D11, MOSI is D10, and cable enable is D22. Okay. Now, according to Raspberry Pi, there technically are only 4 valid pins here. Okay. It's like 10, 11, 18, and 21 or something like that. I mean, I can look it up. I had it on a browser window. Where was I have that? It's also in like the demo code for Adafruit. It's right in the block of messaging code at the top telling you how to set up SPI. But you have to be careful. There's only, as I said, 4 pins that are technically valid for doing this on a Raspberry Pi. Okay. I got notes from SparkFun and others, but let's see, it's yeah, so GPIO 10, 12, 18, and 21 are the only ones technically allowed to be doing this SPI stuff. Any data pin, you should be able to use it, but I had trouble driving things if it went outside their window of thing. And it could be just my understanding how to set the pins up in the first place to do what they're supposed to do. So for this, I decided just to stick to what they told me to stick to. So now in the code, I come around and there's some other stuff in here that this defines the cable select based off that CE pin. The direction is an output. The value is always true. This sets up the SPI with the clock and the MOSI, right? You can, with this SPI setup, determine speed. That's done with an SPI configure. This stuff over here, this comes from a wiki page on this board. I took it right out of the Arduino code as samples so I can learn how they were doing this, right? Now, another weird thing I found about these LEDs, if you set the pins all to 1, so 4 blocks of 8 bits for a total of 32 bits, if you set them all to 1, it's like it's off, which is kind of weird, because technically to turn a row on, you would toggle the rightmost bit in the thing to 1, and this row would turn on. If you set the rightmost bit to 2, you turn this row on. If you set the right bitmost to 3, both these rows would go on. If you set it to 4, this row would go on, etc., etc. It's in a power of 2 thing. So next time, if you set it to 8, right, the 5th row would go on. If you set it to 16, the 6th row would go on. If you set it to 32, the 7th row would go on. If you set it to 64, the 8th row would go on. Now, adding them together gets you combinations of rows turned on. So in theory, 128, because that's 64 plus 32 plus 16 plus 8 plus 4 plus 2 plus 1, right, will light all the matrix. But once you go past 128 on the row setter register, it gets weird. Now, the columns are done similar, but in combination with setting the column, you're also setting one of, I think you're limited literally 9 colors or 16 colors or something like that, because it seems to me that half the bits that you use to set color and the other half the bits are used to set column. And I'm not 100% sure. This is where I'm starting to get stuck on this, right? So after I've done all this, now I've written some notes in here, the way the matrix works. So the connectors are on the left side over here. I didn't actually write that in there, but that's where they are. A little conversion thing for me so that I know which bit is which. So I know that bit 1 is way over here, but bit 64 is way over here, right? 128 is over here. Okay. The other thing is the 4 registers. So I just keep calling it that, but what the heck? It's color, 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 row. So 8 bits, 8 bits, 8 bits, 8 bits. So when we come down to when we're playing with the code, like right here in this comment, red, blue, green, row. And in this row, I'm turning on the 2nd row, for example. And I'm turning on the column, everything, all the columns, and maxing out the color. So down, what I did down here is I made a loop. I was playing around here. I made a loop right here so that I could loop through the red color. And this is what I'm kind of show you right now, is that this is where I am kind of stuck on the whole thing. Because it's not really making sense to me. I will go down and expand the bottom again because we're going to need the bottom a little bit. So I'm going to recycle the code. Okay. Now I've got the loop on a pause. It's waiting for the keyboard input to do the next increment of the loop. And we're starting at 0. So right now, this thing is loopy 2, 0. Green is 255, blue is 255, and we're doing the first row. You'd think it's this one, no, but it isn't. Because you have to think how the register is, and the shift register is loaded. So we're pushing, for the row, for example, we're pushing 0, 0, we're pushing 1, 0, 0, 0, 0, 0, 0 into the thing. So it's, the 1 was the first thing pushed in all the way on the right side. And then we're pushing in 1, 1, 1, 1, 1, 1, 1. Then we're pushing in 1, 1, 1, 1, 1, 1. And then we're pushing in 0, 0, 0, 0, 0. By the time we've lined all this up, we've pushed 32 bits into the row. And we're now ready to, the CS value, to trip the trigger. It will dump all of it simultaneously out into the system. Okay? So when I go down here and I press enter on this, we can see one row lights up. All of it. So now over here in loopy 2, the value is 0, 0, 0, 0, 0, 0, 0, 0, 0, 1. Okay? And since we seem to have all the others at zeros, right? Remember I said about 255 turning everything off? Well, in this case, we're all zeros except for one. It's like we've got all the columns turned on along with the row, and then we've got the red color, which seems to be like 4 1-bits to it. Now, if I press enter again, now we're on 1. Notice that the first one here, it's kind of hard to see. I wish I could do this better because it's kind of dim. Which you can see in the top right corner camera. You can see that this one right here, where my finger is pointing to, is off. Now if I press 2, press the enter key again to go to the 2 on the row. Now the first one's lit, but the second one is off. 3, these 2 are off. 4, this one's off, these 2 are on. 5, 6, 7, 8. So now the byte array is a value of 8. Okay? So in 8, if we look at our table here, that's 0000100. Now this is the part that drove me nuts trying to figure this out, because at first I thought it was like the first 4 bits in a register were turning color, and the latter 4 bits were turning columns. But that's not the case. Okay? Because if we come back down to here and we go 9, 10, 11, 12, 13, 14, 15, 16, right? You can see this thing is counting in binary, right? Now if we were to turn on values into the other 2 here, so the 255 and the 255, we would get a different color. Okay? So if we wanted to make this thing, right now it's red. If we wanted to make this thing really bright, if I went to here and I said 128, Control S, and I'll restart it again. Oops, there we go. Still red. Now if I change this, for example, to 64, Control S, and restart it again, one of these will change color, but not the very, I have to go down the thing. There we go. It was blue for a moment. In fact, can I see? No. There, you can see blue occasionally popping its nose up in here. Very faint, right there. Like you can see the blue. I got my hand there. See the blue between the reds? That right there? That's actually blue. Very faint. Right? And there it's really distinct blue. And then notice the last one, it's gotten more brighter. I don't have a diffraction piece here, do I? No, not readily. I thought I used to have some diffraction glass here. Diffusing glass. Wow, I didn't realize I had Raspberry Pis up there. No, those aren't Pis. Do I have one? Yes, I do. Right here. So, let's see if this looks better. You can definitely see the blue, red. You can see the tail one is, it's hard. Sorry, I can't really show you this well. It is a little more purple in color. But this is literally the state I'm at with this. I'm stuck at. right, is trying to figure out how can I turn on a particular column, right? I have a row on. Now let's say I want to turn a particular column on all the time. Now I know that up to 128 should be, in theory, 127 should be a particular set of columns. I always thought that if I had the red at 1 and the row at 1, I would only get red on the first corner one. But that's not the actual case here. So we're passing 90s. There's the blues again. So we're approaching 127. 3, 4, 5, 6, 127, all those blues are on. 128. Now, once we go past 120, the whole thing starts decreasing. The amount of red lits. And every so often, the blues show up. So we're in the 242, 45, 47, 49. Now we just started the whole thing over again. I've got too many keys in the keyboard buffer. So that's what I'm sitting at right now, my problem. And this is why for users, I do not recommend messing with this panel. I know it's cheap on AliExpress, but I think it's a bit of a blind alley for easy use. It just is very hard to control things on it. The patterns they made in the wiki and that, I understand how they made them, but it's just very basic. But figuring out how to actually do it wasn't explained at all. They just say, oh yeah, just turn these bytes on with this value, right? And you can see that in the arrays here for example, heart, right? They tell you that we're going to write 1, 2, 3, 4, 5, 6, 7, 8 bytes worth of data, and each byte value is this. So every one of these things can have a value of 0 to 255, right? So this stuff you're seeing here is in hexadecimal, so it's 0 to FF, right? But you can write 0 through 255 and 255, decimal values. The system doesn't really care, of course. But this is where, and then they would run a really weird loop here. I think I have a sample of that loop. Yeah, they would do this. And notice that they're saying, first byte in the array, but subtracted off 255. Then leave alone the second array and the third array, either the registers, and on the fourth array, that's the row. And they bit shift this. This is what the two left greater signs are doing. So they're playing with bit shifting in there too. I mean, it's not easily explained and not easily done. So I'm sorry, but this is the limit I can tell you about this, because this is the limit I know on this thing at the moment. There are better ways to do this. Now, let's stop this code for a sec. And I'm going to actually run it one more time just to turn off the LED on here. There we go, and stop it. Now, we have here this one. It's almost the same size, slightly bigger, but these are neopixels, right? They also run on an SPI system. Or actually, not even that as much. You don't really need SPI to actually run them. You just need a data pin. So currently I have this hooked up to the Raspberry Pi on the 5 volts, and I have the data pin on number 21. So what we're going to do here is we're going to go to a different set of code. This one. This is your stock. Oops. This is your stock NeoPixel code. Basically, what it's going to do is do some rainbows and stuff like that. We just have to change our pixel pin, or the one we're actually on. So I'm going to put this on 21. And it's an 8x8, so we have 64. So this guy is treated like a big snake. So here's the in, right? So what's happening is it goes like this, then like this, then like this, then like back, then this way, then that way, then this way, then that way. So in essence, it's one big long row of pixels. So let's see what happens when we run this one. Oh, we have an error here. Okay, it was needing sudo command here. I wonder how you give it sudo command in here. Well, we can do this outside of the editor for the moment. I would have to actually figure out how you do this. I never thought of that. Okay, so I know this is test.py. So if we go and we say Python, you can say Python or Python 3. It doesn't really matter. Because Python, I believe, just linked to Python 3, but I'll do Python 3. And we do test.py. Oh, sorry. Sudo all this. And now we go back to our this. You can see. Oh, where's my diffuser thing? There you go. So it does this 3 colors, does a rainbowy thing, 3 colors, rainbowy thing, and it's going to loop forever running. And as you can see on this one, it requires really no effort to do this. If you're going to play with LED matrices like this, these small ones like this, these are the better ones to use, not these. A lot less code to drive this. And if we go over to our this, you define time, board, and NeoPixel. You define a pixel pin, a trigger pin, number of things. You do have to need to know if this is going to be green, red, blue, or red, green, blue. There are different ones of these have the different one. Some of them have an extra white pixel in it. So make sure you just get the right one. Then all you do is you set up a the NeoPixel guy right here, and you set up parameters: pin, pixels, brightness, auto write, and pixel order. And then there's just you play with the loops and stuff like that, like this. This is the one that's showing the colors. And this is rainbowing. And it's fairly straightforward code to run this with just these. And it's easy. You get started right away. And this will apply to single NeoPixels, NeoPixel strips, NeoPixel grids. What it doesn't apply to is... let me get one off the shelf here. So to a third style of grid, and that's this. Okay, so this style of grid here, and it's effectively like these. These are all 3 colors in here. This is an RGB matrix. This is known as, I believe, a P2.5 64 by 64 matrix panel. Okay. And it uses what they call the Hub 75 interface. So some of these pins in here control power and stuff like that. Others control what they call data pin A, B, C, D, and sometimes E. In this case, this does have an E, right? And it divides the panel into sections, and when you send signals down the A, B, C, D, E lines, things light up. And there's code for this too. So, but the little guys like this, and by the way, these little guys come in all sizes. I've got them as 2x2, 3x3, 4x4, 8x8, right? I got them round, like it's in a circle, right? You can get them in rings, right? All types. And of course, when you're in strip form like these, right? There's tons of strips you can do. You can get from the manufacturers. This is a plain Jane strip. In fact, this particular strip I have here, not this one, I think, its other half, because it was joined together. I actually chopped it in half. This is 72 pixels. Right, actually I was using this one, 72 pixels. But I did find that this one, there's a shoddy connection somewhere in here. Now, I'm not 100% sure it's a shoddy connection, because this is the type of strip that you have to be very careful in the Raspberry Pi, because I cannot direct drive this strip with the Pi's 3.3 volt. That's where that level shifter comes in. I have to actually, the green wire on here, which I believe is the data thing, has to be driven with a level shifter. And that's what this is all about here, this gizmo here. And then we have in among this gizmo, I soldered up this. So this connector breaks out into pins, this. And what I was doing is I was sending the data in here and getting the power from external. As in one of these devices here. You screw them in, you get a barrel jack, and you get power from a standard power supply. Now there's also ones like this. Same thing, same idea. Everything is the same as this one, except this one has cables pre-soldered on it. And these come in 8x8s, 8x16s, 32x32, I think 32x64. They're all types. You can get all types of those. So now, as I said, I cannot give you more instruction on this because I still don't understand this one enough. And this is why it's been on the back burner for so long. I wanted to do stuff that was a little more productive. And we were working at work with what's called MQTT. It's the protocol used by IoT devices to talk back and forth. So you would have an MQTT client over here and a broker over there, and you would send commands to it. So you could set up a microcontroller on one of these LED matrices and send commands to that microcontroller and say, turn on your lights, turn off your lights, do, stuff like that, right? And for some reason at work, one of the guys wanted to use a Pi to do all this. And I think the Pi for doing stuff like this is an overkill, right? It's convenient having the OS, but I think having the CircuitPython on the microcontroller and the way it works is easier to deal with than the Pi is. But that won't stop you doing it. I mean, just pointing out that, in my humble opinion, that was a little overkill for doing it. I mean, a whole Pi just to drive an LED strip. I mean, I still have the thing rigged here to a Metro M4. This is where the code originally came from. right? But I think if you're going to do something like this, use something like this. And even this one's a little more feature-ridden than features than you normally need. Like, I mean, a Pico would do the job just fine, right, to drive all this stuff. So here's, for example, a digit LCD, and I've just tacked it through the I2C bus to a feather. And told, this is an RP2040 feather? Yes. And it's easy as pie to make these, do digits and whatever. And once you get into I2C, another limitation is removed. This, on SPI stuff, only one device can be on that SPI side. That's it. If you need more SPI devices hooked up, you have to have more SPI devices. Now, by default, Raspberry Pi only enables one. But you can read the documentation, and there is a section dealing with how do you enable more SPI devs on it, and how do you use the overlay system in the the boot directory to do all this. And you can effectively set up multiple SPI buses on here. I think they talk about setting up at least 4, but I2C is better, because I2C devices, you just have to have unique IDs on them, and you can daisy chain. And I did this already in a previous video where I chained, like, I don't know, was it 21 devices in a row? And they were all working. Wow, this thing is real bright. So let me go to the console screen and break the code here. So I'm just going to pull the power on this. There. Yes, it's just stuck at the last day. You have to remember these little LEDs in here actually have a microchip with them too. That's how they. You're sending a bit command to the microchip, and it's going to tell it what colors to be. And this one will let you definitely do like 255 colors, right? And you don't really need pulse width modulation for any of this either. That's another thing you're supposed to be able to do with these ones. You just control the brightness level of a pixel with PWM, but I've never gotten that to even work properly. Now, Adafruit does have a 595 shift register library, but I could not get it to chain 4 of them together correctly. So I kind of gave up on that code. So I hope this, for you, the guy asked the questions, helps you anyway if you still want to pursue this. But I do highly recommend you just. This is to myself, it's a toss in the bit bucket type of LED matrix. It's a puzzle to be solved, but I only have so much time, and I come home and I'm kind of tired and I don't want to work on anything, so I find these a lot easier to play with. So I will cut this recording at this moment. If you really want, I honestly won't want. I don't want to go back into this guy anymore. I will go into other code for this. If you need more details on the Raspberry Pi setup, as I said, it's basically works. Oh, you might have wanted this in a different language like C. I could have done it in the C code in the Pi, but I didn't do it. I would have to set myself up for C compiling, and I haven't done that. It's all there. Oh, and the other one is you can hook this up to a true Arduino, let's say Uno or something like that, and drive it. I have done it. You can also do MicroPython. That's where I got the code idea for this. It was actually from the MicroPython code. I converted it over to CircuitPython. So that's another way you can do this too. Well, I will let you go, and I got chores to do, and that's it. Where's that stop button? There it is.